So the problem statement goes as follows. It is a 220 volts, 200 ampere, 750 RPM. That is what is given as the DC motor's rating. RA is 0.05 ohm. And TL, that is the load torque, which is given as 50 minus 0.25 N, where N equal to speed in RPM. Okay? And it is given speed above base speeds are obtained by IF control. That means V is held constant at rated value. Right? And speed below base speed or rated speed. This is obtained by VA control. And I am assuming IF is held as a constant. Normally that is how it is done. Okay? And what is being asked is calculate VA and IA when speed is 400 RPM. So the first thing is calculate VA and IA when speed is 400 RPM. That's what it starts with. Okay, so first of all, let us try to calculate it under rated condition. Right? So let me first solve for it for rated condition. So for rated condition, 220 minus 200 multiplied by 0.05. Right? This is going to be my EB. Right? And I can also calculate. So this is for rated condition. So under rated condition, first of all I can calculate what is EB at rated value, and I can also calculate TL, which is 500 minus 0.25 multiplied by N. So N is 750. Right? How much is it? 312, whatever, 312.5 Newton meters. So I can also say if my IA, it's a separately excited motor, so I don't have to worry about, bifurcating IA into IF and so on and so forth. So I can simply say, so this is separately excited, because of which I can say torque constant at rated excitation. This is only at rated excitation. Okay? So under that condition, I should be able to say 312.5 divided by IA. IA is 200. This will be KT, whatever is the value. Okay? Fine. Now I have to calculate at 400 RPM what is VA and what is the value of IA. So let me say this is A, this is B. Oh, what am I saying? This is A. This is what I am calculating. Okay. So let me try to calculate what is the value of, first of all, armature current at 400 RPM. So I should first of all calculate what is the load torque. Load torque at 400 will be 500 minus 0.25 multiplied by 400. So this will be 100. So 400 Newton meter. Right? That is what is the torque. If 400 Newton meter is the torque, I should be able to calculate the current, armature current, by using the torque constant. With the torque constant, I should be able to calculate the current. So I should say IA will be 400 divided by whatever is my KT. That should give me the current. So this is IA at 400 RPM for this particular load torque. The moment you solve for IA and I have the speed as 400 RPM, I should be able to calculate what is the value of VT. VT will be EB plus IARA. So EB I can calculate. So EB at 400 RPM and at rated excitation will be same as that of whatever is the EB value I have got earlier. Either I can use that and I can say 750 by 400 by 750. I can do it that way. Or I have the KT, torque constant, which will also be same as vacuum. It is not coming out to be the same. Okay. So maybe there is some problem in terms of the problem formulation itself. So if it is not coming out to be the same, then you can do it. See, even if you had done it that way, I could not have questioned. Or if you try to do it as EB at 750 multiplied by 400 divided by 750 will give me EB at 400. I can do it that way too. If I have EB at 400, then I have to multiply this, add to this. If I call this as EB dash, then I can say EB dash plus IA dash RA, where IA was whatever I calculated using the torque constant. So this will give me what is VA at 400 RPM. Okay. So I must have followed a similar thing for the other one also, where the field control is being implemented, where I am going to assume that the voltage is maintained constant at rated value, right? Is that clear? Okay. You can do that too. So that's why I'm telling you, as long as you follow one of these methodologies, I cannot question it. Right? Because we normally assume that KT and KE are the same, as long as you use the speed in radians per second. Right? So that is fine. Okay? Is it fine? So if this is the confusion, then I think both methodologies are valid, because sometimes some of the problems, you know, have some amount of discrepancy unless it is deeply looked into. That's the problem. Right? So the problem formulation itself was a difficulty there. That's the reason. So in the case of synchronous generator, we said basically that we are going to have either a permanent magnet or electromagnet in the rotor, which will be rotated at synchronous speed, and when it is being rotated at so-called synchronous speed, if it is a 2-pole machine, it will be 3000 RPM. If it is a 4-pole machine, it will be 1500 RPM. Armature will have 3-phase conductors located in the inner periphery of the stator, and you are going to get induced EMFs in all the 3 phases corresponding to 120-degree phase shift from each other, because they are placed at 120 degrees away from each other. So let us say I have basically a machine which is going to have the voltage induced to be E equal to 4.44 F5 multiplied by the number of turns multiplied by the winding factor. This is what we talked about in the last class. The winding factor comes up because the windings are distributed and it may have short pitching. If you have to learn more about short pitching, please look at the appendix of PC Sen's book. Okay? Maybe page numbers around 570 and odd. Okay? So you might like to look at that. So this KW actually will be equal to KD multiplied by KP, KD being distribution factor and Kp being pitch factor. These are going to be the 2 factors that will be involved. This is definitely true even in induction machine if I am using it as a generator. If at all I am using an induction machine as a generator, this has to be true, definitely. And we are not really talking much about this when we were discussing induction machine, because we never talked about it as a generator much. That's the only reason we didn't talk about it. But otherwise, this is the induced EMF equation for a synchronous machine. Now, if I have multiple number of synchronous machines that are all connected finally to the grid, right? The grid is generally like an ocean. When I compare to the grid, when I compare with the grid the capacity of any individual synchronous machine, the individual synchronous machine is going to be a drop in an ocean, basically. So we call the grid as an infinite bus. The grid is generally told or called generally as infinite bus. We call it as infinite bus because the voltage and the frequency of this grid are kind of set in stone. They are not going to change. If I say that it is a 400 volts, what I am getting in my laboratory from the grid, it will remain by and large at 400 volts. It can deviate very, very little. Similarly, the frequency, if I say it is 50 hertz, it should remain at 50 hertz. The maximum deviation I may have is from 49.5 to 50.5. Generally, I will try to maintain the frequency and voltage normally because so many of them are actually pouring their power into the infinite bus, and all of them are working at a particular value of voltage and frequency. So you would hardly see any variation that is coming up just because maybe one load is added or one load is subtracted. That is not going to make a big difference in terms of the voltage and frequency. It will make a difference if I try to probably remove n number of generators completely from the grid. If I am going to have the grid supplying, let us say, X megawatts, and if I am going to remove so many generators which are corresponding to probably some Y megawatt, where Y is almost comparable with X, even 50% or something, then there will be a power imbalance. I hope you understand. There will be a huge power imbalance. What I am trying to say is, let us say X megawatt is my grid generation. And I am going to have, this is exactly met by the load demand. I am having load demand on the grid. I am going to have also as X megawatt. Suddenly out of X megawatt, if I just minus some Y megawatt, that is I remove so many generators from the grid. Maybe there is a fault. Maybe the generator stopped functioning. All of them not functioning is very rare. But let us say something happened and I had to remove. When we remove this, what will happen is there is a power imbalance, right? Because of which this load, unless I have to shed the load. What I mean by shedding the load is removing the switch which is connecting the load to the grid. Let's say I have connected my entire supply, my household supply to the grid. That is through a fuse. If I remove the fuse, it is opened up. That's all I'm talking about. So if I shed many loads, then if it becomes, the load also becomes Y megawatt, it is perfect, X minus Y megawatt, it is perfectly fine. Rather than that, I have not removed my load. I have just left my load. I have not realized that so many generators have conked out, right? In that case, what is going to happen is, whatever are the generators that are working already, their kinetic energy will be kind of depleted. The kinetic energy that are stored in the form of kinetic energy in the rotating parts of the machine, slowly that will get depleted. So what is going to happen is, the steam turbines or hydro turbines which were rotating this particular machine, they have only a finite capability. They will not be able to provide more and more power than what they were providing. So what is going to happen is, slowly the kinetic energy that was stored in the rotating parts will be converted into the electricity, and then it will try to feed the load more than what it is capable of. But in the process, the speed will come down, definitely. When the speed comes down, the frequency will come down. If the frequency comes down, ultimately the grid will collapse. That's what happens sometimes if suddenly one of the complete lines conk out. That is, let us say I have a Dadri power station which is generating a huge amount of electricity which is catering to the needs of Delhi. So in case there is a problem in the switch yard of Dadri power station, the switch yard is the one which will connect all the generators ultimately through a transformer which will step up the voltage and back to the grid. That's what it is going to do. Let's say there is some problem in the switch yard. So maybe many circuit breakers have opened. So none of the generators from Dadri is being connected to the Delhi grid. So what is going to happen is, if people have not noticed and they have not switched off many of the loads in Delhi, which is a power guzzler normally, if that is not done, then you are going to see that eventually it turns out to be unstable condition, because the frequency will fall, because the speed will fall, and eventually it will become extremely unstable. The entire thing conks out. A few years ago, I don't remember, maybe 2010 or 2011, there was a major power outage because of the entire northern grid collapsed because of the HVDC link, high voltage DC link, which is actually coming from Rihand, which is near Varanasi, which is feeding power to Dadri. From Dadri, we guzzle up the power. That DC link conked out. Because it conked out, completely the entire northern grid was in darkness. So what I am trying to tell you basically is, the infinite bus is infinite as long as I think things are all fine. If many of them conk out, many generators conk out, or many loads for some reason conk out, which can also happen if one particular feeder is stripped completely. Feeder is a transmission line which feeds power to some industrial area probably. So something conks out, I'm going to have a power imbalance. If there is a power imbalance between generation and load, I'm going to have either the speed increasing enormously or speed decreasing enormously. If the generating station realizes many loads have been shed off, then they have to reduce the amount of steam that they are pumping into the steam turbine. Right? If they see that more and more loads are coming up, they have to notch up the steam that is going into the steam turbine, so that the power, the speed is a constant, the torque is the one which they are changing by inputting different amounts of steam. That's all they are doing. The speed is a constant. The speed will not change whatsoever unless there is a power imbalance. So on the whole, whenever I connect a generator to the grid, it is a very tedious and long process. That process of connecting a generator to the grid is known as synchronization. So synchronization of a generator means that I am connecting a generator to the grid, and the grid voltage and frequency are set in stone. So I have to modify basically the voltage if it is not matching, if the frequency if it is not matching, I have to modify only my generator. I can't expect to be modifying the infinite bus. That's not possible. So let us take a look at what is the process of synchronization. So first of all, we talked very briefly about OCC or open circuit characteristics the other day, which we actually said talked in greater detail in a DC machine. Even in synchronous machine, it is almost similar. So OCC is the voltage generated per phase or line to line voltage, either way is fine, okay, versus IF at synchronous speed. So if I say that at synchronous speed, if I am running my prime mover and I am trying to look at what is the generated voltage versus field current, that gives me the OCC. So let us say I have the OCC somewhat like this. So this is going to be my EG and this is going to be IF, and I'm talking about the OCC, which is probably going like this. Okay? So maybe at a particular value of IF, right, I am getting actually this EG to be approximately rated voltage. Let's say my machine is rated for 400 volts line to line or 230 volts per phase, whatever. So I'm measuring maybe line to line voltage, and this is 400 volts line voltage, RMS value. So this field current is generally termed as the rated field current or rated excitation. This is going to be my rated excitation or rated field current, and I'm generally assuming that IF and flux are not really linearly related, but they definitely are fairly linearly related until my operating point is arrived at. I will not operate it much beyond the saturation generally. I will try to operate it just before the saturation. So this is my field current. So what I'm trying to get at is the voltage magnitude can be adjusted by adjusting the field current. That's all I'm trying to get at. The voltage magnitude definitely can be adjusted by adjusting the field current. And frequency can be adjusted by adjusting the speed. So I have two specific controls in the generator. One will be excitation control, which will play around with the magnitude. So, okay, this is related to the magnitude of voltage. And the second one is speed. The speed will be controlled by adjusting the prime mover speed itself, and speed control will adjust actually the frequency. So whenever I want to synchronize a generator with the grid, I have to definitely look at these things first, whether they are matching or not. So for synchronization, actually I will look at majorly four performances or four performance parameters. One is the magnitude of the voltage, which I can definitely adjust with the help of the excitation. The second one I will check is phase sequence. I hope you understand what I mean by phase sequence. I may be generating ABC in my generator. Maybe the grid is in ACB, or I am thinking that what is my B may be actually C, and what I am thinking as C may be actually B. So I don't know. So if I just close the switch and connect it to the grid, I'm gone. The generator will be completely burnt out. I can't afford to do that. Are you getting my point? Because when I'm talking about the grid voltage, maybe it is VB is actually Vm sin omega t minus 120. Maybe my B phase, what I am thinking as B phase in my generator will be Vm sin omega t plus 120. I can't connect definitely the two. Then it is like a line to line short circuit. I'm trying to short circuit two different voltages, which is deadly. So I can't really do it if the phase sequences are different. Yes. The generated voltage depends upon the speed as well, no doubt. But if I have already brought the frequency up to 50 Hertz, I would not like to play around with the speed. Very good question. Obviously, you are going to have the voltage magnitude dependent upon frequency as well as flux. If I have already brought up my frequency to 50 Hertz, I would not like to play around with it. Then what should I do? I will adjust IF. Both of them play a vital role, no doubt. But mainly I am going to look at the excitation because it will not affect the other parameter. That's the reason. Right? So I have to match the phase sequence as well. If the phase sequences are not matched, I'm going to have a big problem. The third thing I have to match is the frequency. The frequencies of both the voltages should match. If they are not matching, maybe I will see that at some instant both the voltages are matching, after some time there will be a phase difference. Let me draw two waveforms. One is probably at 50 Hertz. This is, let us say, the grid voltage waveform. If I have another one at 49 Hertz, I will have basically the phase shift between these two slowly and steadily increasing. I hope you understand. One is omega 1t. One waveform corresponds to sine omega 1t. The other waveform corresponds to sine omega 2t. So if I try to look at what is the difference between omega and omega 2, that omega 1 minus omega 2 times t is going to keep on adding further and further as the time progresses. So I have 50 as the frequency in one waveform, 49 as the frequency in another waveform. So I'm going to get 1 Hertz as the difference in the frequency. So I'm going to have 2 pi multiplied by 1 multiplied by t as the accrued phase difference between the first waveform and the second waveform. So I have to match the frequency as well as phase simultaneously. All four have to match. The voltage magnitudes have to match. The phase sequences have to match. The frequencies have to match. The phases also should match. But phase and frequency are highly dependent on each other. So this process generally is automated in most of the power stations, where I have to synchronize actually the generator to the grid. That is automated because you are talking about hundreds of megawatt. So you don't want to do it manually and commit a blunder and have the whole thing blown over on the top of you. So that's the reason why it is generally automated. But what we do in the laboratory generally is done manually. So let us probably slightly take a look at the synchronization process, how it is done for smaller generators. From the generator, I have 3 terminals, which are the armature terminal. Here is my grid. I'm going to show this as the grid, from which also I'm getting 3 terminals. What I'm looking at is to close these switches. This switch is closed. This is the second switch which I want to close. This is the third switch which I want to close. So these switches are synchronizing switches. What I'm trying to do is to connect the generator to the grid directly. If the two are not matching in every way, it is like short circuiting 2 different voltage sources. Whether the frequency is different, phase is different, phase sequence is different, whatever I do, I have, actually if you look at it here, this is one of the voltages. So this is probably V of the generator. Okay? And this is the V of the grid. You see that at this point there is no difference at all between the 2 voltages. So you can close the switch. That's fine at that point. But if I try to close the switch here, you can see that between these two there is a huge amount of voltage difference. If I try to short circuit a huge amount of voltage difference, I'll very clearly see a huge current flowing. What is the resistance between those 2 points where I'm trying to close the switch? It is literally 0. So the current will be infinitely large. So when I am trying to close the generator to the grid, I have to make sure that the voltages at the terminals of the generator will be exactly similar to what are the voltages at the grid point. Otherwise, I will have a huge amount of short circuit current that will be flowing through the generator into the grid, and the generator will conk out first. That's what is going to happen. So I can't afford to do that. So when I am synchronizing, generally in the laboratory, what we try to do is, I have the generator here, and let me show the generator basically with the 3-phase winding. That's it. And I'm going to have the field winding here. What we do in the laboratory is with an electromagnet. It is not done with the permanent magnet because I want to be able to adjust the excitation. So this is going to be my IF. Okay. Now I have, these are the 3 terminals of the generator. And here is my mains, which is actually in the laboratory again. This is equivalent to the infinite grid. And I'm going to normally measure the voltage here and measure the voltage across the generator terminals. If the two are not matching with each other, I'm going to adjust the excitation until I'm able to see that both the voltages are the same. So voltage magnitude matching is very, very simple. Not a big deal at all. But definitely before that, I would have run this rotor which is coupled to a prime mover in a speed which is corresponding to synchronous speed. So I know also that the frequency is going to be really close to 50 Hertz. Because I'm going to have the grid frequency close to 50 Hertz, I want this frequency also close to 50 Hertz. So first thing I do is to start the prime mover, start the generation process in my machine, and once it is generating, I can measure what is the value of voltage. The voltage should be matched by adjusting the excitation. So I have roughly matched the frequency and roughly matched the magnitude as well. That's what I have done. Now I have to match the frequency. Exactly. Okay? I have to match the phase sequence as well. There is something called a phase sequence indicator. You can use a phase sequence indicator. If not, we can even look at it manually and we would be able to say whether the phase sequences are matching. How do we do it? Normally what we try to do is, there are of course the switches here, but even before the switches, we'll normally connect two lamps here. I'm showing the lamp pretty badly. This is two lamps we connect in between the generator terminal and the actual the grid terminal. Why do we connect two lamps? Because normally our machine is going to be rated for 230 volts per phase or 400 volts line to line. So if I put only one bulb, this is all, single phase bulbs. Whatever bulbs we are using normally are working on single phase. That is only 230 volts. If I apply 400 volts, it will not be able to withstand. So it is better to put two of them in series. If you put two of them in series, you are sure that it will withstand that much of voltage if there is a huge voltage difference between these two terminals. Okay? So I will put normally two bulbs each across each of these terminals. I am going to have two more bulbs here and I am going to have two more bulbs here. So these are the lamps. Okay? Now if the frequencies are exactly matching and if I'm going to have the phase sequence also matching and if the magnitudes are also matching and if there are no phase difference between the two voltages, I will have the bulbs not glowing at all. I hope you understand. If the two voltages match exactly, there is no way the bulbs can glow. Right? But it's very difficult, rather impossible for me to get the exact matching like that. Because I may think that it is 50 Hertz. Actually grid frequency may be 49.98 Hertz. Still there is a small difference. Can't help it. And what you measure as the speed may be 1500 RPM. Actually, the indicator shows it is 1500. It can be 1498 for what you know. Measuring error there can be. So what we will look at is, actually, if I am having two of these supplies, one is omega 1 T, the other one is omega 2 T. Right? Two supplies I have, one is from the generator, the other one is from the grid. One is sine omega 1 T, the other one is sine omega 2 T. When I am actually looking at the difference between these two, that's what is coming across the bulb. So I am going to have sine omega 1 T minus sine omega 2 T. This is what is coming across the bulb. Right? So if I say this is This will be essentially omega 1 plus omega 2 will be one component, omega 1 minus omega 2 will be another component. So omega 1 plus omega 2 will be a very, very high frequency, so I will not be able to see actually the intensity increasing and decreasing at all. But omega 1 minus omega 2 I would be able to observe with my naked eye, because it is really going at a very, very slow frequency. If I say 49 hertz and 50 hertz, it is 1 hertz difference. So the rate at which the sinusoidal wave is increasing and decreasing will correspond to sine of omega 1 minus omega 2t. So the bulb intensity, the light intensity will increase and decrease in a sinusoidal fashion. It will look as though it is in a sinusoidal fashion, but it is proportional to I square. So even in the negative half cycle, it is going to give, there is nothing like a negative intensity. It will give only positive intensity. So you will be able to see the light is glowing and coming down in its intensity and so on. If the rate at which the intensity is increasing and decreasing is fast, that means omega 1 minus omega 2 is large. If the rate at which the intensity is decreasing and increasing is slow, that means I have almost matched omega 1 and omega 2 very, very well. So I have to continuously observe the lamp and adjust the speed slightly. If I adjust the speed, maybe I am thinking that it is running at 1500. I have increased it to 1510, 1515 RPM. I am seeing that maybe the intensity is very fast. It is actually increasing and decreasing very, very fast. That means I have gone in the wrong direction. So I have to come back. What we do in the laboratory is to use a DC motor as a prime mover. So DC motor speed control becomes very important from that point of view. So we try to adjust the speed of the prime mover, which is actually my DC motor. By adjusting its field or armature, I will try to adjust the speed. I will go either in higher than 1500 direction or lower than 1500 direction, depending upon whether the intensity with the variation of intensity becomes faster or slower. That is going to actually decide whether you are going in the correct direction. So it may become in such a way that it is actually going, painfully slowly. You would see it going through the change in variation of the intensity. The variation in the intensity will be going through painfully slowly at some point, which is very good for us because that is where our frequencies are matching. So magnitude is matched, frequency is matched. If the phase sequences are the same, the intensity variation of all the three phase bulbs will go hand in hand. Please think about it. If I am going to have A like this, B like this and C like this, right? If I am going to have, this is the A of the generator, this is the B of the generator, this is the C of the generator, right? If I am going to have, let us say, A of the grid, B of the grid and C of the grid, like this, I will have all of them glowing, right? If the frequencies are matching, there is a phase difference. There is a small phase difference. That's what I have shown. The frequencies are matching. The phase sequence is also matching. I will have between them, there is a constant value of voltage maintained. The difference between these two. That's what I have to calculate. So the difference between these two will be something like this, right? This is what is going to be the difference. So all the three phases will have the difference which are equal, almost equal. So we will have all of them glowing almost similarly with similar intensities. If the phase sequence had been different, very clearly I am going to have this rotating in this direction, whereas this rotating in the opposite direction. That's what it means by phase sequences are different. As simple as that. Are you getting my point? Instead of having ABC, if I am having ACB, that means it is rotating in the opposite direction. Definitely I will not have, now I have to look at the difference between A and A, B and B and C and C, very clearly they will be not together. They will not be changing together. They will be actually changing in terms of the difference between A and A, B and B and C and C. They will not be equal. They will not be actually varying with equal intensity and so on. It is going to be kind of stepped variation. Maybe one will go to a high, after that another one will go to a high, and another third one will go to a high after some time. They will not go together. They will not go hand in hand. So phase sequence, we will be able to see that they are not matching if I'm not going to have all the three bulbs varying in their intensity simultaneously. Rather than that, they are having phased out variation. Phased out variation in their intensities. You can try to derive the mathematical expression also. You guys would be able to definitely figure it out. One will be omega 1t minus omega 2t. The other one will be omega 1t minus 120 minus omega 2t plus 120. The third one will be omega 1t plus 120 minus omega 2t minus 120. Try to look at all the three, how the waveforms come up. You would know that very clearly the difference is not going to be, cophasal. They are not going to go hand in hand. So phase sequences, if they are different, only way I can do it is to interchange these two connections. So I have to put this here, put this here. That is the only way out. I have to just interchange two of the terminals. If the phase sequences are wrong, then I can't again change the infinite bus. That is not in my hands. So I have to change only this particular, the two terminals of my generator. Interchange them as far as the connection is concerned. Then phase sequence will match. So now we know how to match the magnitude, how to match the frequency, and how to match the phase sequence. But you can't do this interchanging when the generator is live. So you have to switch off everything, again start afresh. You can't do this when the generator is live. Never do it when it is live. So what you will do is switch off the whole thing, start from scratch, start the DC motor again, bring it to 1500 RPM, bring the excitation to whatever is the rated value, then look at the magnitude, match the magnitude, right? Now you know phase sequence is matching at least, right? So that you don't have to worry. Then match the frequency by looking at what rate this is changing, all those things. Now, at some point, even if there is a small difference in frequency, as I told you, this is my generator sinusoid, and maybe the other one is almost close in frequency, but still there is a small variation. Maybe. Because I'm doing it manually. So I don't know if it is like 49.95 and 50. Still there will be a small phase error accumulated. But at some point the phases will match. Eventually. Because I'm looking at omega 1 plus omega 1 minus omega 2t. So that is essentially going to match at some point, maybe down the line. When omega 1 minus omega 2t becomes 360 degrees, it will match. Right? When it matches, your bulbs will be all dark. At that point, you have to close the switch. So what you have to do is to first voltage magnitudes have to be matched. Then the frequency will be matched. Make sure the phase sequence is matched. Phase will not still match in all probability, but because there is a small amount of frequency difference, the phase keeps on changing. At some point the phases will match. There is no other way. Omega 1 minus omega 2t times t will become 360 degrees or 2 pi radians at some point. Wait for that point where all the three pairs of bulbs go to zero intensity. Just close the switch. That's what we do in synchronization. Right? So synchronization of the alternator is a big process, and all four have to be matched. If all the 4 are not matched, we will have definitely, a huge amount of problem in terms of 2 different voltages getting connected. That too, imagine generator is going to generate about 20 kilovolts. Generally, generating voltage is not more than 20 to 30 kilovolts. We use a transformer to step up. So we transmit it at either 465 kV or 440 kV, 765 kV transmission lines are there. So we are going to step it up. After stepping up, it is actually connected to the grid. So you can't afford to make a mistake there. You're talking about 700 and odd kV. So it's deadly if we try to connect it without proper synchronization. So for this, generally we use something called synchroscope in the power station, which actually would check automatically everything and then connect it. Okay.